You ever stop and think about that? You click a link, and a website from halfway across the planet just appears. It feels like, well, magic. But here's the thing, it's not. See, the internet isn't some fluffy cloud up in the sky, it's a real physical system, a massive global machine built to move information. So today we're going to follow one single piece of data on its wild ride, from your computer to the other side of the world.
And the hero of our story? It's the bit. Every single thing you see online, a song, an email, this explainer, it's all made of millions and millions of these simple ones and zeros. They're literally the atoms of our digital world.
Now this might blow your mind, but something like 99% of all international data doesn't travel through satellites. No, it travels through these massive fiber optic cables laid on the ocean floor, physically wiring continents together. It's a World Wide Web in the most literal sense. But before our little bit can even dream of crossing an ocean, it has to get out of your room first.
All right, so let's pull back from that massive global view and zoom all the way in, like right into your room, because the very first steps of our bits journey depend entirely on how your devices are physically connected.
And this whole layout, it's got a technical name. It's called a network topology. Basically, just think of it as the local roadmap for all your data. It's what defines the paths that let your computer, your phone, and your TV talk to each other, and of course, to the wider internet. So let's break down two of the big ones. On the left, you've got the old school bus topology. It was simple, yeah, but it had some major problems. And on the right, the star topology, which we'll get to in just a sec.
So this bus setup, man, it was a total house of cards. Everything was hooked up to one single shared cable. If that cable broke anywhere, game over. The whole network went down. And even worse, if you didn't cap the ends with this thing called a terminator, the signal would literally just bounce back and forth, creating total digital chaos. It was cheap, sure, but it was not reliable at all.
Clearly, we needed a better way to do things, and that brings us to the star topology, which is almost definitely what you're using at home right now. Instead of one shared cable, every single device gets its own dedicated line to a central hub, which is usually your Wi-Fi router.
And the upside here is massive. So if my laptop cable gets chewed up by my dog, your phone, your TV, they don't even notice. The rest of the network just keeps humming along. The flip side, though, is that central device, your router, becomes a single point of failure. If that box dies, everything connected to it dies too. Still, it's a huge step up in reliability.
Okay, our bit knows the local map, but what are the actual roads it's traveling on? What's it made of? So when it comes down to it, there are really three main ways we send these bits flying. We can shoot them as pulses of electricity through copper wires, like an Ethernet cable. We can flash them as pulses of light through super thin glass fibers. Or we can broadcast them as radio waves through the air. That's your Wi-Fi. And out of those three, it's fiber optics that are the true heavyweight champions of the modern internet. It's just mind-boggling, right? These tiny strands of glass, each one no thicker than a human hair, are the superhighways carrying almost all of the world's data, just by bouncing pulses of light across oceans. So how in the world does a beam of light stay inside a glass cable for thousands of miles without just fizzling out? It's all thanks to a cool physics principle called total internal reflection. A pulse of light zips into the glass core in the center. That core is wrapped in a different kind of glass called cladding. When the light hits that boundary, bam, it doesn't leak out. It reflects perfectly inward, like a mirror, just bouncing its way down the cable for miles and miles with barely any loss of signal. It's just pure physics. Okay, so we've got the roads. But how do we actually, talk on them? How do you turn an abstract 1 or 0 into something a wire or a beam of light can actually understand and carry?
Well, the most basic way is through something called encoding. For a copper wire, it's pretty simple. We just agree on a rule. A little zap of high voltage means 1, and low or no voltage means 0. Send a super fast sequence of those pulses, and you've got a message.
And it's the exact same idea for wireless, just with a different medium. Instead of voltage, your router is translating those ones and zeros into different radio wave frequencies. Your phone picks up those waves and translates them right back into bits. So how do we make sure everyone can use these roads without causing a huge mess? Well, there are two main strategies. First up is baseband. Think of a standard Ethernet cable. It's like a one-laned country road. Only one car or one signal can use it at a time. The whole road is dedicated to that one trip. But then you have broadband. This is your multi-lane superhighway. It can carry tons of different signals all at once, each in its own lane.
That's how your cable company can send you internet, TV, and phone service all through the same single wire.
Okay, we've got trillions of these bits zipping around the globe every single second. How on earth do we stop it from becoming one giant planetary traffic jam? We need traffic cops.
The old school method was called circuit switching. Remember old movies where a telephone operator physically plugs in a wire? That's what it was like. They created a dedicated private line just for your call. It worked, but man, was it inefficient. The internet uses something way smarter: packet switching. Your data gets chopped up into thousands of tiny little pieces called packets. Each one gets a destination address slapped on it, kind of like a little envelope. They all get shot out into the network, take whatever path is fastest, and then, like magic, they're all put back together in the right order at the other end. It's brilliant.
And what about the flow of traffic on these paths? Well, half duplex is like a walkie-talkie. Over. You can talk or you can listen. You can't do both at the same time. It's a one-lane bridge where cars have to take turns. Then there's full duplex, which is what we're all used to today. It's a two-lane highway. Traffic flows in both directions at the same time. You can download and upload simultaneously.
Okay, this brings us to three super important terms that people mix up all the time. Let's clear it up. First, bandwidth. Think of this as the potential of your connection. Using our highway analogy, it's how many lanes you have. A 10-lane highway has more bandwidth than a 2-lane road. Next, throughput. This is what you actually get. It's the real-world performance. You might have a 10-lane highway, but if there's a traffic jam, only 2 lanes worth of cars might be getting through. That's your throughput. And last, latency. This is all about delay. It's how long it takes for a single car or one bit of data to get from the start to the finish.
And that brings us to why latency is such a huge deal. Just look at the jump from 4G to 5G. Yeah, 5G has more bandwidth, but the real secret weapon is its incredibly low latency. We're talking a drop from around 50 milliseconds down to as low as 1 millisecond. That tiny slice of time is the real game changer. It's what could unlock the future, things like remote surgery or self-driving cars that need an absolutely instantaneous response.
So let's recap this crazy journey. We followed our humble bit from a simple 1 or 0, navigating your room's layout, flashing through cables as pure light, getting chopped into packets, and being expertly routed across the entire planet. We're constantly making every single step of that physical journey faster, more efficient, almost instantaneous. So I'll leave you with this. What happens, what becomes possible when a journey that crosses oceans becomes so fast that it feels like magic all over again?